and 12:33 at the time. All right, so now, oh, let me get my phone reactivated and connected. Nice. We should be good to go again. All right. Oh, good. Got another one from 122 from James. All right, James, but hang on. Let me switch back over to the questions. All right, so what are the questions? Let me get started for you guys. Okay, number 29. Let's work on that one here together. All right, so number 29, let me read it here. It says, consider a thin spherical shell of radius 14 centimeters with a total charge of 32 microcoulombs distributed uniformly on its surface. Find the electric field. Okay. Let me draw a picture. And so this is kind of thin. So I'm going to take by that. Oh, and I forgot to share my screen. I was going to say, hey, let me draw a picture, but I also got to share my screen. I did get my phone going, but I didn't connect and share my screen. Nice. All right, so let me take it again. Let me draw a little circle representing the shell. I'll even put maybe a radius of capital R in my drawing. And of course, they say capital R is 14 centimeters. It does say a total charge, so I'll put a Q down here for total charge of 32 microcoulombs. And it's distributed uniform. And it looks like it's a plus 32, so I'll put little plus signs here. Now, I think it's safe to say the way they described it without an inner or outer radius, and they use the word shell, that it's really, really thin. And so there is no real distinction between an inner and outer radius. Everything in the real world obviously has a thickness to it. So this is maybe more mathematical, but very close to something that would be very, very, very thin. Okay. And I think the point here is Gauss's law. So let me begin the problem by writing Gauss's law. And so the flux in a closed surface, okay, must equal to the charge enclosed or inside of that Gaussian surface. All right. So here's the physical picture with an actual physical surface and a charge. And what this says is you can pick a surface. Now, as we read the numbers, they ask for the electric field at 10 centimeters. So that would be inside of the sphere. And then B at 20 centimeters. So that would be outside. So I think that we need to do Gauss's law twice here. Let me do Gauss's law, say, on the inside first. So I'm going to make a blue Gaussian surface here. Let me describe the Gaussian surface as little r, as opposed to later on, I'll do a Gaussian surface bigger than capital R. Okay? But as you hopefully will see, there's not much difference between a Gaussian surface of little r and big R. But I'll, again, just want to do little r here. And for any of you who were around before the break, and for that matter, any of my videos, but especially the lecture part of this, the first step in using this technique is to do the dot product. And so going back to physics 121, the dot product means, take the magnitude of the first vector, so there's E, magnitude of the second vector, so there's dA, and multiply that by the cosine of the angle between them, okay? So here's the beauty and the pain of Gauss's law. You need to discover the electric field. That's the whole point you're doing the Gauss's law. And to do that, you have to know something about the angle. So you have to get that from a symmetry argument. And that's what I was starting to say before the break. We did some long ones. We did number 47 and number 55. And both of those, I start off the same way with Gauss's law and start this argument. And I'll start it again here. Let me draw a line of symmetry. So I'll just draw the line that goes through the center here. And that is a symmetric line. And what I mean by that is if you took everything on the left of the line and everything on the right of the line and you switch them, so you kind of flip this whole thing over. Imagine starting here and just kind of flipped it over. What would you get? And now if you're looking at the charge distribution, you get exactly the same charge distribution. So what does that mean? Well, it means something like this. That, and again, there's two ways to argue this. I did one in the lecture. I've been doing both of them here on the Zooms. Why don't I do both again? I'll start this time though with the one I did from lecture. Last time I was doing it the other way around, but all right. So this time I'll start with the one from lecture. Here's how I argued it from lecture. I said something like this. What if the electric field at this point along this line of symmetry was off at some angle other than the line of symmetry? Okay. And you flip this. Well, what would happen is your electric field would be pointing in the other direction. I suppose another way of saying the same thing is what if you just had an observer on the other side? You would see the electric field this way, they would see it this way. Well, it's the same charge distribution once you flip it. So it's physically impossible for each of you to see the same charge distribution, but the result of that, the electric field, to be in a direction that is different. That just doesn't make any physical sense. So what we know is that the electric field would have to be along a line of symmetry. See, along the line of symmetry, when you flip it, you still get along the line of symmetry. And what that means is you do this and you get the same charge distribution, you should get the same direction to the field. And the only way that can happen is if you're along a line of symmetry. Now, another argument that I've been doing in the Zooms, and not the lecture, was something like this. If you take the part that's, say, below this green line, and it made a field, say, in this direction, then since the charge above the line has the same symmetry, it would kind of make the same effect. And the components that are perpendicular to this line of symmetry then would cancel off. And the result of these two, that is the charges below and the charges above, the result of these two would be along the line of symmetry. So whichever argument you like best, here's the result. That anytime you see a line of symmetry for our charge distribution, we know the electric field must be along that line. Now, I drew them pointing radially outward. Please know that they could be pointing radially inward. And those are our two options, and which, of course, they each correspond with whether or not the charges are positive or negative. So we've, by human definition, have said that we know they have to be along a line of symmetry. That's just the way it's required by nature. Now, that being said, we don't know whether it is radially outward or radially inward. But that's fine. We don't pick that per se. We define that with the charges. See, the reason both options are there is because nature has both options. Nature has a positive and a negative. And so both options, but they have to be along that line of symmetry. Anyways, so if they're positives, we by human definition have conveniently called that outward. So I'm going to draw mine outward because I also drew my charge as positive. And that's what we know for this problem. We know for this problem, the charge is positive. They even say, oh, what was the number? I think it was 32. Yeah, 32 microcoulombs, and it's positively charged. So it's got to be radially outward. Now, watch this also. There are many lines of symmetry. I could draw this line. Any line that goes through the center would be a line of symmetry. I could draw this line, that'd be a line of symmetry. I could draw this line, that'd be a line of symmetry. And so all of these are lines of symmetry. And so I'll say it again. Our argument is that we know that the electric field would have to be along a line of symmetry, and we know it would be outward because it's positive. So my green lines here, which I drew as lines of symmetry, I will now say also then represent lines of the electric field. This is what the electric field would have to look like. There's no other option. Now, here's the great thing about that. Because I'm trying to solve this integral and I need the angle between the electric field and the area vector. And I just now figured out the direction of the electric field. So if I can also figure out what the direction of the area vector is, I can get the angle between them and actually then solve this integral. And so, of course, I'm thinking about this Gaussian surface, which is a sphere. And so the dA is perpendicular to it. Maybe if I draw a dA, it would be perpendicular to that blue Gaussian surface, which would be the same direction as the green one, which is the electric field. So I guess what I'm really saying is I know both the direction of the electric field and the dA, they both are radially outward. And so the angle between them, this right here, is 0 degrees.
And that's true for any circle, right? As long as it's going radially outward?
Well, if the charges are evenly distributed, because remember, I'm going to flip it over.
Yeah, okay.
Yeah, so like if I had more charges below the line than above the line, I flip it. Now I have more above than below. I don't get the same charge distribution. I don't have symmetry.
Yeah. Okay, thank you.
Yeah, and probably don't want to solve that one then with Gauss's law. Probably want to go back to the last chapter with Coulombs law or something like that. Now, maybe this is hard enough, so maybe I should be careful staying bringing this up. But if the bottom part was all negative and the top part was all positive, when I flip it, I may not get the same thing, but I get the same thing, just the negative of it. And I could do that same argument that would say then the electric field would have to be perpendicular to a line of, then we call those lines of anti-symmetry. And so we like to say electric fields are perpendicular to lines of anti-symmetry. So if you flip something and the charges, the distribution is the same, but all the positives become negative and all the negatives become positive, then we know it would have to be perpendicular to a line of symmetry. But we're not going to do anything like that this chapter. So I just throw that out as a freebie. But we are going to do lines of anti-symmetry when we get to magnetism. So it's not too far ahead of us. I think we do that chapter. Well, magnetism starts in 29, but I don't think we see that till 30. But when we get to chapter 30, you're going to hear me say lines of anti-symmetry. Okay, but back to this problem. So these are lines of symmetry, and that's a big step, a very big and important step to know that angle, especially since cosine of 0 is 1. So that just, we don't have to think about the cosine factor anymore. Now, there's another part of this first part of Gauss's law that's just as important, and that is right here with the electric field. The electric field's inside the integral. And when you first look at this, you're saying, you're going to ask me to do an integral of something I don't even know? I can't do that. And you're right. If you don't know it, you can't do it. However, there is something we can say about the electric field. And let's realize that the math is saying do the electric field not everywhere, but only on the Gaussian surface. So only on this blue line. So if I kind of picture myself on this blue line, maybe right here, and I look at the charge distribution, compare that to when I'm somewhere else on the blue line, maybe here, or maybe here, or maybe here. And you will hopefully notice that anywhere on this blue line, if you look at the charge distribution, which let's say this is it, you would see some charges maybe above you and then off to the right and above you and off to the left and then down around behind you. But that would look exactly the same as if you were any place else on this Gaussian surface. And since it's the charges that make the electric field, you can argue that although I don't know the equation for the electric field, I do know that the magnitude of the electric field is the same value everywhere along this blue surface. And so you're asked to do an integral, not everywhere, you're asked to do an integral only on the Gaussian surface, and you just argued that the electric field would be a constant, or at least its magnitude. Its direction would be radially outward, but its magnitude would be a constant, and because of that, and the fact that calculus allows us to pull constants out, we can actually remove the electric field from the integral. And now we don't have that problem of saying, hey, you're asking me to integrate an equation I don't know. No, I've gotten it out of the integral. And I'm asking you to integrate something else. And I would say something you do know. So those are the two big important steps that we get from the physics of the problem, not so much from the mathematics. Problems like flux that you see in your math class, you probably don't solve using any of the physical properties. You use all your mathematical properties. But here we're going to ask you to solve these problems using not only math properties, but also physical properties. And so getting the fact that the angle is zero, getting the fact that the electric field is a constant is argued from the physics. It's argued from where does the electric field come from. And those are big steps. And I would even argue probably the biggest steps of the problem. Because if you don't do that right, then you don't justify getting to this point. All right. So now I've justified getting to this point. Now I can actually then do the integral. So let's take a look. This integral, which I won't even actually do the integral. I'll more read it than do it. This says, it's an integral. It says add up the area of the Gaussian surface over the entire surface, the entire Gaussian surface. So what you're going to get here is the entire area of the Gaussian surface. And the Gaussian surface is this blue sphere. I didn't really draw a sphere. It's kind of hard to do that in 2 dimensions, but this is a cross section of a sphere, and the area of a sphere is 4 pi r squared. And so I'm not going to really do calculus. I'm going to just go back to my geometry and say, well, what is the surface area of a sphere? And so again, this is probably, well, I wouldn't describe it as doing the physics, but I wouldn't describe it as doing the math. I'm not really doing the math. I'm reading the math. So it's certainly more math than physics, but I'm saying, what does that mean? And so I started what looked like a hard problem. I mean, it had a dot product, it had vectors, it had calculus, and all it did is turn into geometry. And so that's crucial, okay? Now I'm going to write this just one more time. Charge inside Gaussian surface divided by epsilon. Okay, so now we can come over here and say, all right, let's do the right-hand side. The right-hand side means the charge inside by the Gauss, enclosed by the Gaussian surface. And so this blue line around here doesn't enclose anything. All the charge is at this bigger radius, which I called capital R, at 14 centimeters. So I guess I would have to say, well, 0 is how much charge is enclosed. And the only way that can work is if E equals 0. And I hope that the fact that we got 0 doesn't make it seem like this was a trivial problem. But what it tells us is that inside anywhere, because I could have drawn my Gaussian surface at any r and still got a 0. So at any radius, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, and this problem asks for at 10 centimeters. So for A, at r equaling 10 centimeters, if I were to draw r at 10 centimeters, I would get an electric field of 0.
Could you explain why it would equal 0 for the charge?
Oh, okay. I think what you mean by that is conceptually, because I just explained it mathematically.
Yeah.
Okay. So, all right. So let me, I'll call this page 1 and probably come back to it, but let me try a conceptual explanation. Yeah, because Gauss and others, including Newton, first did this with gravity and was like, whoa, is that right? I mean, you tell me if the earth was hollow and I was anywhere in the hollow, I would get no gravitational force. And yeah, you do. So it works out with gravity and it works out with electric fields. And here's why, conceptually. You just saw why it did mathematically, but that's not always very satisfying. So let me redraw the charged sphere. Let me pick a random point somewhere in here. Maybe I'll pick this point right there. I'm not picking the center on purpose, but let me backtrack to the center. If you were at the center and you say drew a horizontal line, I think you can see that the charges on the top would make fields down, and the charges at the bottom would make field equal and opposite up, and the net field would be 0 in the center. So back to page 1, when I got the electric field equal to 0 everywhere inside, that was a little bit of a surprise. Most people aren't surprised that the field is 0 right in the center. They go, well, yeah, there's equal amounts of positives on the left and on the right. But this point right here, they're a little more surprised. They're saying, are you telling me the electric field is 0 there? I'm closer to these guys, far from these guys? And yes. And here is, I think, a good way to describe it. Draw a line through that point and just cut the circle or the sphere at these 2 points, okay? And then do that with a second one. It doesn't really matter what angle. Oh, yeah, it does. Sorry. Let me draw that again. Okay. Here's the charges. Draw a better set of lines. Put a bunch of charges on a sphere. I'll pick a random point right there. I'll draw a random line through there. Let me mark the center again. All right, so I'll just put a little dotted line down the center for a second. All right, so this random line then I've drawn, I'm going to draw a second line that is exactly matching the first one. And what I mean by matching is this angle that this random line tilts from the diameter is going to match this one. Okay, so now let's look at this random point in the middle, which, again, your question is, that random point has an electric field of 0? Not just the center point? Yeah. But remember my argument for the center point. My argument for the center point is I have equal amount of charges above and below it, and the two are going to cancel off. I'm going to make that same argument here, but it's a little harder. Watch this. Let's divide this circle into 4 pieces. Piece 1, piece 2, piece 3, and piece 4. Now, the easier one is 1 and 3. 1 and 3 are exactly equal above and below the diameter. So it's a fair argument to say that all of these charges in area 1 and all of these charges in area 3 are going to cancel off above and below this line. The harder one to completely buy is 2 and 4. Because you're going to look at this and say, well, you are closer to the charges at 2 than the charges at 4. Yes. But I would also say the charges at 4 are greater.
They're further away.
Yeah, they're further away, but a greater number of them.
Okay, so would this work for any point inside for a uniformly distributed charge?
Yeah.
And
So
you can also any shape that's symmetrical, like if it's a circle inside of there, like how we do the Gaussian one at 10 centimeters.
okay, but the yeah. So pick any point, and then a bunch of those points would make a whole Gaussian surface. But yeah. I think we're saying the same thing. Yeah. So yes. So anywhere in there, the electric field is going to be 0.
Okay, thank you.
So that's kind of the conceptual argument behind it. But I'll jump back to the page 1 now and say, well, mathematically, you can see that as long as the Gaussian surface R is less than the charges at 14, so any radius less than 14 would give you 0. So 10 is what they're asking for, but it would work at 11, it would work at 12, it would work at 40, oh, not 14, but 1 or 2. Anyways, so I think you see my point. So this is to say you would get no electric field anywhere inside and specifically at 10. All right, now, well, I called this one page 2. Let me put it aside. Let me then call this page 3. Page 3 here. Okay. And now let's essentially ask this question. What would be different in all these steps if we were drawing a Gaussian surface that is bigger than 14 centimeters? Well, I guess I would start with Gauss's law. I would do a dot product. The lines of symmetry would be all the same. So I would still say the angle's 0. The distance away is all uniform. So I would say the electric field is a constant. So I'd still get that. I would still interpret the integral as the area of the Gaussian surface, which would still be a sphere. So it would still be 4 pi r squared. So this would be the same. Now, I guess it might be a little different because now I'm talking about an r that is greater than 14. Whereas before I was thinking of r's that are less than 14. But as long as you're still thinking of r as the radius of the Gaussian surface, this is still the same. So that hasn't changed. But here's where it does change. Charge enclosed. See, now that we've incorporated the whole spherical charge, there is a charge enclosed. See, when r was less than 14, it didn't enclose any charge, so I put a 0. So for this second part, B, let me put E 4 pi r squared charge inside over epsilon naught right here. And let me not put a zero this time. That's where it's going to change. Okay. Fortunately, it's not real hard because then what the charge inside would be the total charge of that shell. And so they tell me that it is 32 microcoulombs. So when I go to solve for the electric field, I would bring the 4 pi over and the epsilon naught. I would have the 32 times 10 to the minus 6, and I would divide it by r squared. And so that's definitely not a zero. In fact, now I can do this. The 1 over 4 pi epsilon naught is the same as Coulomb's constant. So that is 9 times 10 to the 9 newtons square meter over Coulomb squared. This is 32, and it was micro, wasn't it? 32 micro, yeah, so 10 to the minus 6 coulombs over, I should probably be a little careful with my units. No, it's Coulomb constant is in meters. And they stay at 20 centimeters. So let me put, and 20 squares the number, but it squares the units. So meters squared would cancel with meters squared. And one of the coulombs, not both, but one of them would cancel off. So you're going to be left with newtons per coulomb at the end, which is great because that is the unit for the electric field. And so now grabbing a calculator, I can go 9 times 10 to the 9th times 32 times 10 to the minus 6 divided by 0.4, I'm sorry, 0.2 squared, which is 0.04. And I get 7 and I'll just put 20 times 10 to the 1, 2, 3, 4, 5, 6. Yep, double check. And so 7.2 million newtons per coulomb would be the electric field. And let me jump over to the author's solution. It's easy to make a mistake here and see what they got. So A, they got 0, and B, they got 7.19 times 10 to the 6th. Perfect. Oh, and then they go on to, and I probably should, they say, don't forget the direction, which we argued earlier on, that this is radially outward. Nice. That help? Jump back over here to Zoom here. All right. Good. And let me switch back over here. All right. So I forget who asked that, but hopefully that helped. I'll move on to the next one and point out again, if anybody's from 121, you get priority.
I have a quick 121 question.
Okay, go ahead, Elizabeth.
Okay, so it's about scaling, and I watched the one about like the pizzas, and it kind of makes sense, but I was wondering if you could explain it with like, can I share my screen really quick and like show you like,
yeah,
he gives us like,
yeah. Okay, did you we're cutting out a little bit, but I think you said share. You want me to give you permission to share here?
Yeah, I
Okay.
just
Let me
wanna
stop
know-
sharing.
okay.
And can you share now that I stopped? Or do I got to change the
Um,
settings?
Yeah, you gotta
Okay.
allow
Yeah,
me
here we
to
go.
do it, yeah.
All participants. Okay. I
Okay.
think now can you share?
Yeah.
Okay, awesome.
So I was just curious if you could put, like, he explains things here, and I watched your pizza, and it all kind of makes sense. But I was curious if you could put it into like these kind of terms. Like he kind of gives. Why can't? Okay. Yeah, he gives those, and I was curious if you could like explain it in that way too. Instead of
Yeah,
just like, yeah.
I'll gladly share. In fact, let me grab your, I think I remember seeing that on the homework. So I'm going to go to your Canvas page.
Okay, I also have this one here that we could use.
Oh, that one's okay. All right, let me wait. Don't. Okay, yeah. Let me switch over to my bigger screen. Oh, nice. I'm gonna screen grab this. Hang on. Because when I start doodling on my pad, I want to turn off your share one, if that'd be okay. Paste. Good. Okay. So I have that question here, and it says a small aquarium in the shape of a cube. That's the one you want? That's the one, right?
Yeah.
Yeah. Okay. Let me now that I have it, let me turn you off. And oh, you already did. Okay, thank you. And then I will turn my doodle pad back on. I think it's helpful if you guys kind of see what I'm writing and doodling. Okay, good. So here's my doodle pad. Let me just put here 121 scaling question. And it says here, a small aquarium in the shape of a cube has a volume of V1. Okay, so V1, which, by the way, I'm sure he gets to this later on in the problem, but that would be length one times, cubed. So length one times length one times length one. Okay, then a large aquarium, so volume number 2, which would be L2 cubed. A large aquarium, which is also a cube, has a volume of L2. The length of the sides of the large aquarium are larger than the sides of the small aquarium by some scaling factor. Okay. So he doesn't really say what the factor is, but he is trying to say this, that a scaling factor, so this F sub L, is how much bigger is L2 compared to L1. And it doesn't sound like you had any troubles with that, but I'm just going to pause there and say, that's the definition. So does that make sense?
Yeah.
Okay. So that's one of our goals, I guess. Question number, so we've got 2 questions off to the right, and question 2 is to find this. Okay. Now, here, let me invent another scaling factor. I don't know what symbol to use, but and he doesn't even use a symbol, so I guess I won't. But if I went volume 2 divided by volume 1, that would be a scaling factor comparing their volumes. Now, since your instructor didn't give this any kind of symbol, let me not also, or let me do the same and not give it a symbol. But I'm going to use this information from up here. So in place of volume 2, I'm going to put V or L2 and cubit. And over here, I'm going to put L1 and cubit. Now I'm going to go back to my Algebra 2 class and realize that when I have a cube of the top and the bottom, that's the same as just the ratio and the whole thing cubed. Now, I think this might be your question, is this right here is that definition of his scaling factor based upon length. So this would be F of L, and it would be cubed. And this would be the ratio of the volume 2 to volume 1. And I'm really tempting to call this scaling factor of volume.
Okay.
But
Yeah.
he doesn't.
Yeah. That makes a lot of sense. And that, yeah, that definitely, yeah, I wanted it just to be put in like the terms that he used like before. So yeah, that honestly, that answered my question, seeing it like that. I just couldn't like, but yeah, you can keep going. I just,
Okay. Okay.
Yeah.
I'll keep going. And in this problem in particular, so I'm kind of inventing, because I don't see it in his problem, this little symbol, scaling factor based upon volume, which is V2 over V1. So I'll keep this around because that's what he does. Is connected to the scaling factor based upon length. And that's what he gets in the last step. I'll do one more step. If I take the cube root, I will get the scaling factor based upon length is the ratio of the volumes to the 1/3 power, cube root. So if I was doing, say, problem number 2 up there, problem number 2, you're asked for the scaling factor of the length. In other words, you're asked how much bigger is length 2 compared to length 1 when they give you volume 2 compared to volume 1. So if I put in a number here, you've got 36,426 cubic centimeters for volume 2. And you've got 13,279, oops, I forgot, it's cubed, centimeters cubed for volume 2. And that's this ratio. I'll raise it to a power of 1/3 in a second. But just that ratio alone, 36,426 divided by 13,279 would give me a number of 2.743. This is how much bigger the second volume is compared to the first, or what I might call scaling factor based on volume. So the second aquarium is 2.7 times bigger in volume than the first one. But then to do how much is it longer, I would have to say, take this ratio and raise it to the 1/3 power. So 2.743 raised to a power of 1/3 is the scaling factor based upon length. In other words, how much longer is aquarium 2 compared to aquarium 1. So I'm going to take that number and raise it to a power of 1/3. And this would be about a 1.4. And so for the numbers you gave me, and I see a number down below it and it's checked off. So you must have gotten it right. Is that what that means? Nice.
Yeah.
Yeah.
I was just getting a little jumbled with like which like factor, whatever. Like I don't know, but that explains it.
Yeah, no, your question's great because one thing that is an important skill to develop, especially in 121, and you know, it takes a while to develop this skill. So I'm not going to say that you'll learn it all the way through, but as you go through these 3 physics courses, a phrase I like to use is make sure you're reading the math. That is understanding what these numbers are. And I kind of think that's what this question's coming down to. So here's what I would say. If I was reading this map, I would say that, okay, looking at scaling factor due to length, I would say that in terms of length, in terms of the aquarium's length, the second aquarium is 40% longer. It's 40% taller. It's 40% deeper. And so its length is 40% more than the smaller aquarium. However, when I'm talking about the amount of water I have to put in this aquarium, it's not 40% more water. It is 274% more water. There's almost 3 times, right? 300% would be 3 times more water. This aquarium, in terms of volume, has 3 times more space for the fish to swim around in. Even though its length is only 40%, it's not even double the length, but its volume, the place for the fish have to swim around, is 3 times bigger. And so they have a different scaling factor because when you make it longer and it's a cube, you're also making it taller and deeper. And so the volume factor goes up much, much more. In fact, it looks like a cube more compared to the length. So if you were to double the length, maybe I'll draw a picture here. I had an aquarium that looked like this. So here's my aquarium. So this is my small aquarium, it's a cube. And I then said, well, let's get an aquarium that is increased by 2. Now I have to be careful. Wait, when you say increased by 2, do you mean the volume's increased by 2, or do you mean the length is increased by And so I'm going to say, well, let's do the length. Let's say that I want an aquarium where the length factor has doubled. So this problem says 1.4, but I'm just going to show a picture of doubling. I would say, well, okay, so if the scaling factor of the length goes up by a factor of 2, since the scaling factor of the volume goes like the length cubed, this would be 2 cubed. And the volume should go up by a factor of 8. I can get, the fish have 8 times more space to swim around. And I think you see that if you do this. So here's my aquarium. So I'm going to double it by putting twice the length. But I'm also going to go up because I'll have twice the height. And then I also have to go twice the depth. And I don't know if I did a good enough job drawing in 3D. But can you see that there's 8 boxes here?
Yeah.
Box 1, box 2, box 3, box 4. Anyway, so doubling the length would make the volume 8 times bigger.
I see now. Okay.
So that's why volume has a different scaling factor than length, but they're tied together mathematically.
Right.
And in fact, for my own fun, if you will, it sounds like you've got this, but I'm going to go back to your problem 1 and say, all right, so what we learned when we derived this right here was that the volume 2 divided by volume 1 is equal to the length factor cubed. So the problem I just was trying to draw is I was saying if I were to make the length factor, this number, go up by 2, I would make the volume factor go up by 2 cubed, which is 8. And that's what problem number 1 is. You're making the length go up, not by a factor of 2, but you're making the length of the aquarium increase by 26%. How much would that make the volume go up? And so 1.26 raised to a power of 3 is twice as big. So even though you only made the length 26 times bigger, you've made the volume, the space inside, go up by 100%, double the size. And so if, as the numbers have, volume 1 is 13,019, and you double it, let's see, 19 becomes 38, and 13 becomes 26. So this would be 26,038. Yeah, well, there must have been some rounding here. Oh yeah, see, I should have used a little. Anyways, without rounding. So I got the same number that you got. Nice. So we both get a green check mark.
Awesome. Okay, that was awesome. Thank you so much.
Sure, my pleasure. That was a good one. Yeah.
I'm gonna head out, but thank you.
Oh, okay, that's all you got. You're
Yeah,
welcome.
that was it. Thank you.
All right, good. All right, let me come back over here to the chat here again. Okay, good. And I'm going to say the same thing when we grabbed Elizabeth that Oh, wait, where did my chat go? Oh yeah, I started a little bit late. So, okay. So anyways, we've got 2 questions in the chat from 122, and I'll continue on there, but I just want to give a shout out to anybody in 121. This is your magic time, if you will. This is the time where you get to the top of the line. And of course, anybody who's around in 121 and 102, you know, once I get started on these 122 questions, they can be a long time. So I just want to make sure I give you guys a chance to ask those. All right. Since I don't see anything coming my way, let's go to the next one. James, it looks like yours is. What do you say here, James? You say, explain why capacitance. Oh, are you doing capacitance already? Decrease in series using the motion of electron. Ah, okay. All right. Maybe I'll start with it as a math description. Oh, and let me write this down. 122 capacitance question. What time is it? 1:29. Okay. So you're way ahead of the class, and that's good. And I'll answer that. See if this makes sense. The definition of capacitance, C, is the amount of charge you have to put on these plates to bring it up to 1 volt. Okay. So just as a review, I know this isn't your question, but just kind of give me some thinking here. If I make a capacitor that has plates, maybe I'll try to give it some 3D look. Okay. Let me do a little better. Here's the plate 1. I'll put a little electrode right here going back. Here's plate 2. The electrode right in the center going back. I like that better. Okay. Now, when I put a electron or a couple, so I'll put an electron on this plate, it chases other ones off, okay? And the capacitance is how much charge do you have to put there to generate 1 volt, okay? Or maybe to put another way, that if you hooked it to 1 volt, how much charge would get there? Okay.
Because there's like a field being created.
Yeah. So if I drew the field in here, it would go from plus to minus. So it looked something like this. Okay. And maybe the conceptual way of explaining it here is if I hook this to a battery. There's the negative end of the battery. Here's kind of the knobby positive end of the battery. And they're not 1 volt batteries aren't very common. I think you have to go to a science store to get a 1 volt battery, but let's just pretend we have one for a second. So I take a 1 volt battery, it would put a certain amount of charge on there, okay? And so if you take that charge and divide it by that 1 volt, that would be your definition of capacity. Okay, so let's say we do that with this capacitor. So it has capacitance C. And let's say we have a second one also. And it's identical. Okay. If you were then to hook them, and this is the heart of your question. In series. The electrode. Here's the electrode. So that's one capacitor. And when you hook them in series, they would look physically something like this. Am I still on the screen? Okay, good. And let me then hook it to that same 1 volt battery. But watch what happens here. It's kind of interesting that this electron, so the one electron that comes off goes onto this plate. Okay. It chases an electron off of here and puts it on here. And that's kind of the key step. It's kind of like this one electron coming out of this battery is doing double duty when they're in series. Because it put a negative here and forced a negative on this one also. And then chases one off and does like that. Okay. Now, the fact that we've got two of them, so a field would get formed in here, and since they're identical, an identical field and charge would be the same there, but it's the two of these together that got to add up to 1 volt, not separately, but the two of these together add up to 1 volt. So essentially, what you have here on this one is half a volt. If you will, you could say you have half as much charge. So only half as much charge came out of this battery to go on this plate compared to when you did it here.
When you say charge, we're not referring to like the charge of the electron, right? Because that's the same.
Yeah, I'm referring to basically how many electrons. So each electron has a charge of 1.602 times 10 to the minus 19. And so,
right, but the one electron came, did the like ping pong ball, billiard ball thing to the other one. So would the charge be double? I see what you're saying about the voltage.
Okay. Let me put some, okay. Let me try to springboard off your question a little bit. Let me come back up to here. So up here, just for the sake of conversation, let's say 100 electrons actually built up on this plate. Okay. So if I were to ask the charge on this plate, I would multiply 100 times the charge of one electron. And so that would be the charge on the plate. But let me change my phrase from the charge on the plate to the number of electrons on the plate. Okay. So I'm going to say, for the sake of discussion, let's say that there is 100 electrons in this scenario. And that 100 electrons made the field strong enough to be 1 volt. Okay. Now, coming to this scenario, as you said, you understood that the voltage would be only a half a volt here. Now, a half a volt is because you have half the field, which means you have half the electrons. So in other words, only 50 built up on this plate.
Okay.
And if you thought of this as one capacitor charged with 1 volt, you would come back here and say, oh, I only have half as much charge. So my capacitance is only half as great. Maybe to put another way here is, remember, capacitance is charge per volt. You hook them like this, because the voltage cascades together, you don't put as much charge on because you're getting the double effect of the voltage here.
Aren't there 50 electrons on the second negative plate as well?
Yes, but let me point out, they did not come out of this battery. See, if you're trying to say, what is this equivalent to? You would say, what came out of the battery?
I'm thinking of capacitance as like the system's ability. What is it? How much charge it can store per unit of voltage.
Per 1 volt, right?
It feels like this one's storing 100 electrons worth of charge. Like I could stick a light bulb at 2 places, right? I could put like 2 light bulbs, like one between the 2 middle, you know what I mean? Those 2 innermost plates, and then one to the left of the leftmost plate. You know what I mean? Like it feels like we've got some energy there in that middle area.
Yeah, I would say what you're not saying is, if you put a light bulb here,
Okay.
you would get 50, but at a half a volt. You would get 50 here, but at a half a volt, which would be the same as if you put the light bulb, or well, I'm going to be careful with using the word same. But what I am trying to say here is, what am I trying to say? That this is not the same as this. There's still 100 here.
Right, so 50 times 1/2 would be 25, and 50 times 1/2 would be 25. So we get 50 whatever out of the bottom, and then 100 out of the top. But I feel like in the capacitance is reduced by a factor of 4 when we double them up, though that might not be correct at all.
No, yeah, because when you do this, so if this capacitance was 10, when you hook them in series, that's equivalent to a capacitance of half as much phi.
Is half as much, really? Okay, so because it's like 1/10 plus 1/10, 2/20.
Be 2/10, which is 1/5.
Yeah, okay, so that makes sense. So I guess
I hope, yeah.
I might say that, sorry, I know I'm like taking a while with this one. It's really abstract.
Yeah.
I guess I'd say that the field is reduced on each, like split in half, because they're both giving some resistance to the battery.
Yeah, and also, and I don't know if you got this far in that chapter, but the energy is a couple of factors, and then it's the field squared. So if the field is cut in half and you square it, that's 1/4 of the energy on each one of these. So it's 1/4 times 2, and that's 1/2. So there's half as much energy in this configuration compared to this configuration.
Okay, that's awesome. I've been like stuck on this one for a while.
Okay. Nice. All right. Good. All right. Well, keep up the good work. Like I said, you're way ahead, so you got a lot of time to think about this before the exam.
Yeah.
Good. All right. Good. All right. So let me move on to the next one here. It looks like, Ren, you say do 57 at some point. All right.
But he's abdicated his seat.
Well, if anybody wants to go ahead of him because he's out, that's fine. Otherwise, I'll do it. Maybe he just wanted to put it on recording, and I know somebody else would appreciate it. So, Dana, if you have anything, otherwise I'll just go on to 57. Number 57. I think he's referring back because before the break we were, or was it 29? Yeah, right. Or it was back at the other time break. We were doing number 55, and I said 55 and 57 were a lot the same, and a little subtlety there. And so I think he wants to see that one too. All right, so let me get it started. What the time is? 1:43. All right. All right, so let's go. I'll put here in case anybody scans across the video. Chapter 24, problem number 57. And like I said, I kind of mentioned that 55 and 57 were a bit challenging because they didn't have the uniform charge distribution. All right, so let me read this one, and I have a feeling this might go a little long too, so I'm going to put a page 1 here. But it says here a spherically symmetric charge distribution. So that was just like 55, has a density given by this equation. Now, let me draw a picture. So here is my spherical charge distribution. And like I was doing for the break with 55, and there was another one there, I think it was 47. Let's call the spherical charge distribution a radius of capital R. Maybe I better keep reading. Charge in the sphere is radius capital R. Yeah. So they're going to use the same symbols. Okay. So capital R. And then the density, the charge density is not uniform. It has an A over R, little r, where little r is a function from the center. If I were trying to get a physical kind of picture of this, I guess I would say something like, okay, when R is really small, the density gets bigger and bigger and bigger and bigger. So it's really concentrated in the center of this and tapers off as we get to the edges. Maybe that would be a good drawing. So really concentrate in the center, and as we move outward, less and less density. Okay, there, less and less concentration. But yeah, and actually, this is a common procedure in semiconductors, because usually when you're manufacturing, you inject or create some kind of charge, and then you let diffusion, let it mingle and spread out, and there becomes a continuum, a function of high concentration to low as the charges get distributed with time before you solidify it or do whatever it is to lock the charges into a permanent position of that. So this is very common diffusion process of our charges. All right, so I'll start again here. A spherical symmetric charge distribution has a charge density given by this equation, where A is just some constant value. Here it says, find the electric field as a function of R. Now, hopefully you saw in the lecture, the reading, or any of the other Zoom problems I did, the 47, the 55, the 29, we usually got to divide this into two pieces. And one of those is outside of the charge sphere, and the other one is inside. Let me not draw the inside one. Let me do just the outside. So I'm going to draw a Gaussian surface such that it has a radius of little r, but little r is greater than big R. So I'm really finding the electric field at this point outside of the sphere. And then I'll do a second step and find it inside the sphere. Now, like all these problems I was doing today, this chapter is teaching you how to use a very powerful tool called Gauss's law to get the electric field. And this is it. So it may sound overly simplified, but would you like to know the answer to every homework problem? Right there. That's it for this chapter. That's Gauss's law. Now, let me this time do it a little bit faster, since I explained it in a couple of other two earlier on and in the lecture, that if you draw a line of symmetry, oh, how about this line right here? And I guess the first question is this a line of symmetry? In other words, if you took all these charges and you flipped it over, would you get the same charge distribution? That's what we mean by a line of symmetry. See, because our charge distribution is a bit more complex than just a uniform charge distribution like we saw in number 47. But this charge distribution is a lot like number 55, although 55, the charge distribution got bigger as we moved out radially. This one, the charge distribution gets smaller as we move out radially. But either way, since you move out radially, if you flip this charge over here would come to here, and this charge over here would go to there, and that would be the same. The heavier concentration of charges right here at the smaller radius would flip over and go to here at a smaller radius. But again, it still would be the same value. So even though the charge density is not what we would call spherically symmetric, it does have a line or a mirror symmetry. And so the stuff on the left matched the stuff on the right. Now, that is my way of saying, yes, this is a line of symmetry. Like I said, a little harder to see that one. But why do I care about lines of symmetry? Well, lines of symmetry have to have the direction of the electric field. Boom. Let me explain. If it didn't, let's say the electric field from all these charges along this line of, at this line of symmetry was pointing off of it a little. If you imagine picking this whole thing up and flipping it, that electric field would now look like this. That is a different direction than it was before. But wait a minute. When I flipped it, the charge distribution is the same. And it's the charge distribution that makes the field. How could it possibly be in a different direction if it's the same charge distribution? So that's our symmetry argument. And that is our argument to say that the electric field then could not be off of a line of symmetry. It must be along the line of symmetry, because when it's along the line of symmetry and you flip it, the electric field doesn't change its direction, as should be the case when you end up with the same charge distribution after you flip it. So that's our argument for lines of symmetry are very important in using Gauss's law, because they tell us the direction of the field. Now, here's why that's important, because our first math step is to take this dot product. And when you take the dot product, one of the things you have is the cosine of the angle between the electric field and the normal vector. And to figure out that angle, you have to know the direction of the electric field, and you have to know the normal vector. And so I just figured out the direction of the electric field. In fact, to be a little more complete, this would also be a line of symmetry. This would also be a line of symmetry. This would also be a line of symmetry. So all these green lines of symmetry are also lines of the electric field. And so I would say in words that I have just discovered from a symmetry argument, the direction of the electric field. The electric field is radially outward. Now, the other thing I have to do is get the direction of the normal vector. See, the dot product means the angle between the two vectors that are listed in the dot product. And the normal vector is perpendicular to the surface. So here's this blue surface. And perpendicular to it would be something like I'm drawing now. It would be in the direction of these green lines, which is radially outward. So the green line, which is the electric field, and now the normal vector, dA, this blue one, these are in the same direction. So that tells me this angle right here is 0 everywhere along on this Gaussian surface. And that's an important first step. Another important step is to justify that you can pull the electric field out in front of the integral. And you can do that for anything that's a constant. And we can justify that the electric field is a constant on this Gaussian surface by kind of imagining us standing somewhere on this Gaussian surface and looking at the charge distribution, and then going to some other point, and it doesn't matter where, but some other point on this Gaussian surface. And if you look at the charge distribution from that perspective, you'll see it looks exactly the same whether I'm here or whether I'm here or whether I'm here or whether I'm here. And therefore, the electric field that it creates would have the same magnitude, magnitude, same magnitude, same magnitude. So that's our second piece of this puzzle that is going to say, all right, because of that, I know that the electric field is a constant. And so those are the first two big steps in Gauss's law. Getting a surface such that you know this angle and you know E is a constant, so you can pull it out. And if you look at the other ones I did earlier, the 47 and the 55, you'll see right away that I spent a long time here doing the same thing. All right, now we can get to the part that is going to involve the density that makes this problem hard. And that happened over here on the right-hand side. So let me do the left-hand side since it's the easier of the two. I'll do it first. The left-hand side would be the electric field. And then this, instead of actually doing the integral, I'll more read the math than do the math. And this just really means area. This says add up a bunch of small areas. When you do an integral and add up a bunch of small areas, you're just going to get the total area. And it's the total area of what? Well, it's the total area of the Gaussian surface. Okay. And the Gaussian surface is a sphere. And so I'll go back to geometry and point out that the area of a sphere is 4 pi r squared. And actually, this might be a good time for me to do a plug. Your survey book, the appendices. Last week, I even sent you a couple of screenshots from the appendices because you had to do one of those Taylor expansions or binomial expansion ones. And so I said, hey, don't forget to look at Appendix B. Same thing can be said here, that don't forget to look at Appendix B. They got a lot of geometry stuff in there. And one is the surface area of a sphere. So this is the surface area of the sphere. Now, this is where I'll pause and go to another sheet of paper because how much charge is enclosed is going to take a little more thought. So let me move this over and say, okay, let's call that page 1. Over here, I have page 2. And let me go to the definition of density, which is a little bit of charge inside of a little bit of volume. And let me use calculus for it, right? And so if I came back here and we draw this charge distribution. Now remember we said right in the center, there is a lot of charge, and it tapers off towards the edges. So lots in the center. Again, that's what this equation, rho equals A over R would tell me, right? The bigger R gets, the smaller the density gets. It's an inverse relationship. All right, well, the reason I did that is because if you imagine then a particular volume, maybe at first here, I'll just draw a cube. I'm going to change that in a minute. And so that's a little bit of volume dV. Inside of that little bit of volume is a charge of dq. And so if I were to write this as dq is equal to rho times dV, to figure out how much charge is inside of that little cube, I would take the density and multiply it by the volume, and that would give me the charge that's in there. Now, what I'm trying to do, let's come back to page 1, is I'm trying to find the total charge inside of this whole Gaussian surface, which is this whole ball. So I'm trying to find out how much charge is in this whole ball. And so I guess I would say what I need to do is to get the charge inside is I have to add up all these charges, right? I've got to integrate this, which means I've got an integral of rho dV. Yeah. In a picture, I guess it would look like this. Once I did the first little cube, I would do another cube and then another cube and 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 another cube. And I would eventually add up all the little cubes in here. And eventually, that's what this is. Take the density where that cube is times the volume of that cube, add it up over the whole ball, and you're going to get the whole charge in that ball. So that's the hard part. Now, let me draw a new ball that I kind of messed that one up. Put a bunch of charges in the center, tapering off, and so just a few on the outside, maybe a few more here. Let me not draw too many charges, though. Ooh, I didn't. No, it doesn't look very circular, symmetric. I'll do that. But what I'm going to do, instead of add up volumes of cubes, because that's really not a good way to do a spherical problem, let me add up shells. And so if you could imagine a spherical shell, I kind of think of it this way. Let's see if I can take a thin piece of paper, and make a spherical shell. Which isn't real easy to do, but I do got a round object here. Okay. So imagine that piece of paper wrapping all the way around. I should probably get some aluminum foil. But if I wrap that piece of paper all the way around, that's what I'm trying to draw here. Trying to draw that the volume of this piece of paper right here is that shell. And so if I take a piece of paper, and that'll be a shell, and another piece of paper, that'll be the next shell, and I add all these shells together, all these volumes together, I'm eventually going to get the volume of a whole sphere. Okay. And I guess I'd have to start with one really small and get bigger and bigger and bigger and bigger. Okay. So here's my two shells, if you will. Okay. So I'm going to say this is the integral of rho, and this is the key point. Volume of a shell. What is the volume of a shell? Well, let me bring these piece of paper, or one of them, back into the picture. So this was wrapped around, not very nicely, but this was wrapped around. If you cut it and opened it up, so there's my shell made flat. What would be the volume of this piece? And this volume then would be the area of this piece of paper times its thickness. So if you come back to this picture here of this shell, the area would be 4 pi r squared. And the thickness would be really thin in terms of calculus symbols. It would be a dr. So this is the thickness dr. And that's going to be added up from a really small shell of radius 0, making the shells bigger and bigger and bigger and bigger. I'll just draw another bigger one out here. So I've got 2 shells in my drawing, but I'm really adding an infinite number of them closer together. I just didn't want to draw them, because if I draw them real close together, it'll make my drawing look crowded. Maybe I'll do it like that. So another one, another one, another one, another one, another one. So the last one has a radius of capital R. And so let's do that. So from 0 to capital R, here's the density, A over R. Here's a 4 pi. Here's an R squared dr. And of course, as we do that, we can pull constants out in front. So A and 4 pi are all constants. And it looks like then we just have an integral of R dr evaluated from 0 to capital R. That would be A 4 pi, and then this would be R squared over 2 evaluated from 0 to R. So this would be A 4 pi capital R squared over 2. And that, I think, is the magical step for this problem. That's the hard one. Figuring out what the total charge is enclosed in the Gaussian surface. And you have to do that by adding up the shells with how much charge is in that shell. So you take the volume of the shell and multiplied by the density, that gives you the charge in the shell, add it all up, and that's the total volume in the shell. All right, so now I go back to page 1. So here's what I diverted from page 1, because I said what I need is the total charge in the inside of this Gaussian surface, which is a whole ball. So I'm going to put that here. So this would be an A, a 4 pi, capital R squared over a 2. And then don't forget that it's charge over epsilon naught. All right, and there is a 4 on each side. There is a pi on each side. So to finish this, I would have an A and a capital R squared here. Downstairs, I would have a 2 and an epsilon naught and a little r squared. Yay. And let me check the solutions here. This is, I think, the last one, 57. And it looks like they only did the inside. Maybe did the outside. He doesn't have an answer for the outside. spherically symmetric. Find the electric field as a spherically symmetric charge distribution has a charge density of, where is it? Find the electric field as a function of R. Huh. Let's look at the answer again. He only gives an answer for inside. Okay. Weird. Am I reading something? Maybe I keep thinking maybe it said only on the inside. That's not how I read the problem. I read the problem that they want us to do is both inside and outside. All right, well, maybe I didn't need to do the outside, but nonetheless, I did. Let me finish the problem then by doing the inside. Unfortunately, there's not much difference. Maybe I'll change colors here. But here would be the difference. If you were doing the inside, you would have done a Gaussian surface on the inside. And everything else would be the same. And I'll put a line right here. Except right here, the charge inside of your Gaussian surface would be different. So this step is going to change. Because what I just did with the Gaussians on the outside is I did the whole ball to get all the charge. But now with a Gaussian surface that's kind of inside of it, you would only add up to the Gaussian surface and then stop. You wouldn't go to the edge of the ball because that's not in your Gaussian surface. And you can indicate that in your math back here by changing capital R to lowercase r, lowercase r, lowercase r, lowercase r, and lowercase r. And that would be an important difference. So I'll put it over here. So this side of the equation would still be E times 4 pi r squared. But this side of the equation would now be an a 4 pi, and a little r squared. That's the difference. And when you go to simplify, the 4 and the pi's cancel off like before, but also the r's cancel. You see, last time one was a capital R and one was a lowercase r, so they didn't cancel off. But this time they do cancel because they're both lowercase r. So you would end up with an a over a 2, and oh, that's the charge. I forgot the epsilon naught from right here. Okay, and then epsilon. And that then would be the field on the inside. So this is inside, this is outside. It looks like we're getting past our break here. So we'll take a break here in a moment, but got to check this out. Is that what they got? Yeah, that's what he gets. But he never did the outside. I feel like I'm reading something wrong. Spherically symmetric charge distribution has a charge density given by rho equals to A over R. Find the electric field as a function of R. Doesn't really say on the inside. So I'm glad I did both. I think we're supposed to do both, but the author and his solutions only did the inside. All right, well, I know these are long, and hopefully they were helpful. And looks like a lot of people are already out taking their break. That's good. I'm going to do the same here and come back at 3 o'clock. So about 48 minutes. Talk to you then, okay? Take care, everyone.